Okay, so today's lecture is again a non-trivial, I would say it's a non-trivial topic today. And it might take some post-processing after the lecture to understand it. I don't know about you guys, but has anybody had the experience that you see something in a lecture the first time and you don't get it, but then when you see it a second time, you do, it clicks? I've had that experience. Yeah. So this could be one of those days for you that you see it for the first time. And it doesn't make any sense. We'll do our best though to make sure it makes some sense. So last time we went over the ray casting pipeline. And we had lots of terms and terminology. Today we're going to go over a new algorithm called the Shear Warp algorithm. And the idea is to increase the processing speed of the traditional ray casting algorithm. So the first version, the first ray casting algorithm, took a long time to compute. And the idea is there something that can be done to accelerate that, to speed up the computation? And that's what we're going to talk about, essentially acceleration techniques. This could also be called acceleration techniques for ray casting. But this particular algorithm has a name called the Shear Warp Factorization Algorithm. So here's the idea, the overview slide. Nobody told me that I didn't switch the projector. I'm surprised. I could have just kept talking. Nobody would have said anything. This is the overview slide. The idea is, in the original ray casting algorithm, you have an image plane, which is where the pixels are being projected, the pixel colors and opacities are being computed. Right here's the person looking at the screen. And the rays could hit the volume, these are the volume data slices, at any angle, right, at any arbitrary angle. And we spent kind of a long time, 1 or 2 lectures ago, on ray sampling techniques. I think that was the last lecture, it was on Monday. And we had this long discussion of ray sampling techniques and number of interpolations every time we took a sample along the ray, and how costly that was. Well, the idea here is, instead of the ray hitting the volume at an arbitrary angle and then resulting in lots of interpolations along the way, it could be 7 trilinear interpolations for a single sample, to shear the data or shift the data. This is a shear operation, and you slide it and you lean the whole thing over, such that the rays are perpendicular to the data samples to simplify the interpolation. So we interpolate every time we hit a slice, but it's always at a right angle. The ray is always at a right angle. So we can do uniform sampling, right, with the uniform distance, and we can always do it when we hit the edges, the edge intersections. So we can avoid the interpolations, those trilinear interpolations in between the edges. So there's a shear step, then there's a projection step, and then there's a warp step, which is it's like an unshear step, right? There are 3 main steps. So we shear the volume, do our compositing, project the intermediate results, and then unshear or warp the resulting image in image space. And that's hard to understand, so we're going to talk about it more. But the goal is to get rays that are parallel to the volume data, parallel rays, and that to derive a one-to-one ratio between voxels and pixels, so that the voxels line up with each pixel. And hopefully that will make more sense. That's the overview. Right. Here it is again, like another kind of overview. So the shear step is rearranging the slices so that when you sample them, they recreate the same sampling as when they're not sheared, so to speak. Right? It's the equivalent of moving the viewpoint back to the front of the slices, in front of the slices. Right? So there's a shear step in X and Y along the X direction and along the Y direction, but not along the depth, right? Then there's a bilinear interpolation in the slices. Then there's a projection step from 3D to 2D. If you think about the Viz pipeline, by the way, that's the same projection step from 3D to 2D as in the Viz pipeline and the volume visualization pipeline. So there's nothing, that is the same thing, so to speak, the projection step. Right? It's compositing based on this principle of one voxel per pixel ratio, right, along a voxel scan line, so to speak. We have more slides that describe these in more detail, by the way. And then there's an extra step. So at the bottom of the pipeline, you're used to seeing projection from 3D to 2D, and then you're finished. That's like the traditional pipeline that we've seen so far. But here we're adding one more step. Because we have a shear, then we have a composite. This is the original one. When we project the shear, when we do shear the volume and then composite to get derived pixel colors and opacities, we have an image that is distorted. It's distorted because of that shear. And of course it's going to be distorted. This is what a human head looks like that's what it's supposed to look like. But if we shear the volume and we do a projection, it gets distorted. That's a distorted human head. So we have to undo that distortion. And that's done with this so-called affine transformation. But it's done in image space. It's like after the projection. So something has changed, right, in the order of operations. So we go from a warped intermediate image in the image plane to the final image, which is called the warp step. That's the third step. And you can I think of it as an unshear, like the inverse of the shear. You're undoing the shear, but it's an image space. Now, not everything makes sense yet, because my psychic powers are telling me, like somebody's asking, okay, I can see that there's a shear step, I can see that there's a projection step, and I can see that there's this warp step. But you haven't said, like, why. And that's true, I have not said why. I sort of said why. I said it's to make things faster, right? To make the process of ray tracing faster. But I didn't say how. I didn't say how, like, that is going to be accelerated. So the whole idea, this is something new. The shear is something new that you haven't seen yet in previous lectures. And the unshear or the warp step is also something new. That's like post-processing. That happens after the projection. But this somehow has changed. We've seen compositing before in the standard ray tracing algorithm from Monday, which is on YouTube, by the way. But now, this is where all the computation is in the traditional ray casting algorithm. This is where all the intense computation is. This is the step that slows down the traditional ray tracing algorithm. And now we're going to modify that, this projection step, so it's no longer as slow, right? And make it faster. So some people missed Monday's lecture, that's fine. You'll have to review that lecture though, in order for this to make more sense. I don't think this is going to make very much sense if you haven't seen Monday's lecture. But just do your best. Oh, luckily I've copied and pasted one of the diagrams from Monday's lecture here. So as a little refresher, in the original ray casting algorithm, these were the sampling. These are rays that are cast into the volume data and that sample that volume data. And we talked a lot about these three different sampling techniques. Right? This is regular sampling, so the distance between samples is uniform, it never changes. Here, the distance between samples along the ray is also uniform, but the samples we take from the volume are not equidistant because we get these jumps sometimes, right? And then we have one that's sort of a compromise in between, where we sample along edge intersections. Now, why is that? It's because regular sampling is the most computationally intensive out of the three sampling techniques because it requires the most interpolations, the highest number of interpolations. So if we hit an edge, we only need one interpolation, but if we hit a center, we need 1, 2, 3 interpolations. 2 along y and then 1 along x, or 2 along x and 1 along y, it doesn't matter. And in 3D, that would be 7 linear interpolations. That would be 7. This requires no interpolation because we're using nearest neighbor sampling. And then to lower the number of interpolations here, we always sample along the edges. So it's just one interpolation over and over again. Right? But we have some extra samples. All that interpolation is costly in terms of computation time. Now, you can use your imagination here, right? And shear this volume. In other words, take the volume and shift it like this. If I take the volume and shift it like this, it turns this ray into a horizontal. You can shift it so that the ray is horizontal. Right? If I pull this one down and I pull this one down, like they wouldn't be pulled down all the same amount. But that's the shear. And what happens is this ray gets rotated, so it's horizontal. So this is pulled down a little bit, it's sheared, this ray is horizontal, and now the ray, since it's horizontal, it just hits the edges of the voxels and always does one sample per edge, and it's uniform. It's also uniform, so it gets the benefits of the voxel intersections without the extra samples, and it gets uniform sampling at the same time. That's the idea. So now we're going to talk a little bit about the details. So in a volume you have 3 stacks of slices, right? Or a stack of slices. The first up is the shear, which I just described. Then there's a compositing, and then there's an warp. Now the compositing can be accelerated. That compositing stage. And this is where the magic, this is what makes it so much faster. Anybody heard of run length encoding before? most silent at any room of students, of people. If I said everybody like meditate, it wouldn't be this quiet. Indigo, you had your hand up first. Run length encoding? Yes, exactly. Exactly. Run length encoding is a form of compression. Anybody know where it's traditionally used? It's usually introduced in a special subject in computer science. A great subject. Not usually. It's used in images as a compression technique, but that's not like where it's really originates from. It's traditionally introduced into in another subject. Anybody have any ideas? Signal processing again. It could at least I learned it in networks, right? Because in networks you have this bottleneck of data transmission. So how do you compress the data so you don't have to transmit as much and therefore speed up your transmission? That's usually where it's introduced. So for example, if I was trying to transmit an image, just a single image over a network, but it happened to be all black. It was just a black image. Every pixel had the value of 0. Well, I could transmit 0 a million times if it was 1,000 by 1,000 image. I could transmit a million zeros. But that's very intense bandwidth. Or I could just transmit the number 1 million times 0 and compress the whole image down to a much smaller number. That's the idea behind run length encoding. Did everybody follow that? What I just said? I could use a whiteboard, but we don't have one. But I could use this. I could use this thing. But yeah. I think everybody here understands run length encoding, the basic idea. Anybody not understand run length encoding? Nobody's willing to admit that in front of the class. So this applies the idea of run length encoding to volume data as one of the acceleration techniques. And it's not very difficult to imagine where that run length encoding is very effective. We've been seeing lots of images of like people and cadavers, right, scanned into a CT scanner or MRI scanner. Well, a lot of that data can be compressed to virtually nothing because it's not interesting, like the air, right? The air can just be compressed into nothing. You don't have to sample, thousands and thousands of voxels of air if you don't want to. You can compress those. So here is the idea, and this is where this is non-trivial as well. So we have our data set that we shear so that at the right angle so that our rays are orthogonal to the volume. And then we have two for loops for all scan lines. Scan lines correspond to a line in the image. So this is a scan line, a line in the image, a row of pixels. Remember, this is ray casting. The traditional ray casting is a image order algorithm. That means there's a for loop that looks like for each pixel do this. That's what that line is. For each pixel do the following. That's the image order part. But then inside there's another for loop for all slices front to back. That's an object order for loop. That corresponds to objects in image space. I'm sorry, object space. Slices from front to back. So starting from the front and moving backwards. So there are two for loops One corresponds to object order, one corresponds to image order. And here's the compression, so skip transparent voxels. That is, so in this image, we have, these are transparent voxels, and we can skip them. In other words, we don't have to sample them. Remember those rays going into the volume and collecting samples? We skip transparent voxels. We can encode them using one-length encoding if we want to. Now this is a slice in object space. And then look what happens. We're skipping, this is a scan line in image space. Now a pixel has color and opacity. A voxel also has color and opacity. So here we're skipping transparent voxels, and then we find a voxel that's not transparent. So we sample it with a ray casting technique, and we project that result onto the image space, right? We composite, we sample the color and the opacity and project it onto the image space and compute a pixel color and opacity, right? That's what's happening here. Now what is happening here? Here we hit a voxel, it's also got a color and opacity, however, it corresponds to a pixel whose opacity is 1. And you have to also remember Monday's lecture. In Monday's lecture, we talked about early ray termination near the end, for anybody that was still awake. And that means as soon as the pixel value reaches an opacity of 1, that if you keep sampling the volume behind that, it can't change the color, because we can't see that far into the volume. That's what we were talking about on Monday. You know, we can't see beyond a certain point because the opacity has already reached its maximum value. It's like if you look into the ocean, you can't see to the bottom. It would be cool if you could, but you can't. At some point, you can only, I don't know, you can't see that far into the ocean because it's not completely transparent. It has an opacity. And at some point, the opacity is so great that you can't see beyond a certain point. It's the same thing here. It's the exact same thing. So these three are pixels whose opacity is already 1. They've reached their maximum opacity, so we can skip them. That's the other acceleration. So the first one was skip transparent voxels, the other one was skip opaque pixels. And now, hopefully you can make that connection between what we're talking about here, skipping these pixels, and therefore not sampling these voxels, and that 1-to-1 pixel to voxel ratio. So that shear step sets up the 1-to-1 ratio. Question?
No, let's finish.
Okay. If you have a question, it's good, because it means you're at least partially following, or maybe completely following. If you couldn't ask a question, then it could mean there's no way you can, you're following enough to articulate a question. Besides, I don't get it. So there are 2 skips. One's in voxel space and one's in image space, and those are the 2 compression techniques being used, or the 2 acceleration techniques being used to make the ray casting faster. And these skips don't happen in Monday's lecture, in the ray casting. We didn't talk about skipping anything in Monday's lecture. We just said, for each pixel, cast a ray into the volume, do your sampling, project the results, done. That was the idea. Here we're skipping transparent voxels. Sometimes we're doing a projection. we're skipping opaque pixels. Here we find a combination where we can't skip. We have to do it. This green arrow means compositing. It means sample the voxel and project the colors and opacities to the image plane. That's what those arrows mean. And skip transparent voxels. Skip opaque pixels. So don't bother sampling. Don't bother sampling those voxels. Composites. So in this particular example, we skipped most of the voxels. We were allowed to skip all these, all these, all these, and all these. And we only composited 1, 2, 3, 6 out of something like 15. So there was a lot of skipping and compression. And once that's done, we have to do our warp, which is the unshear in image space. Anybody understand that? So this is bringing a lot of things together because it's bringing together, well, it's bringing new things like that shear. But I think everybody can understand that, right? That's how you lose in Jenga, right? If the building starts to shear, you lose, right? Everybody understands that. That's not conceptually too hard to understand. And the sampling and the compression and the skipping is more, I think, more difficult to understand. But this is, if you can understand this slide, then you can understand the algorithm, basically. This is like a one-slide pseudocode summary of the algorithm. So if you can understand that. Now the warp, again, this is done in image space, and it undoes the distortion caused by the shear, which so I like to think of it in my own mind as the unshear operation. Now you could be thinking, well, that doesn't make any sense because why would you shear and then unshear, right? Well, this unshear happens in image space. And when you do computation in image space, it's faster than in object space because, anybody know the answer to that question? That's right, it's two-dimensional. There are fewer pixels than voxels. With voxels, you have something like 512 cubed, right? But with pixels, you might have 512 squared pixels. Right? So you have a lot more voxels than pixels. Right? That's the basic answer. Oops. So there is a way to incorporate perspective projection, by the way. So this is a computer graphics topic. Anybody remember that term, perspective projection, from computer graphics? Anybody remember the term parallel projection in computer graphics? Who took computer graphics?
It was 2 years ago.
I know, this is a weird topic.
It's parallel projection where you're sending rays in parallel, basically.
Yes, how do you know that?
I just remember.
Well done, what's your name?
Aston.
Aston, no, I got it wrong. Oh, how do you say it?
Aston.
Alistair. Is that a Welsh name? That name goes outside of my name space. Yes, you are exactly correct, Alistair. I will try to give another explanation. So, it's all about that projection from 3D space to 2D space. How is that done? That can be done in it's typically done in two ways. The easiest and most common standard way of doing that projection is all of your rays are cast from image space to object space in parallel. Right? The angle between them all is infinite. The rays never intersect. They never intersect, so they're all parallel. That's the standard, most common and easiest way to do the projection from 3D to 2D. But that has consequences, and there are two things. That has consequences, and it's not as quite as realistic as what our vision system does. So when I'm staring at Carlo, which I do a lot, I am not, Carlo's projection is not coming back at me with parallel rays. So I have two eyes, hopefully, and each one you can think of as getting a ray from Carlo. But those rays are not actually parallel. There's some distance, so Carlo, he's bigger than the width between my eyes. So when I look at him, the rays are not exactly parallel. Yeah. You could also think of like the rays moving outwards from my eyes a little bit. Right? They're not exactly parallel. They could be moving outwards. If the object's very close, then they're going to be, But this information, so some information gets lost when you make all of your rays parallel. So if you make your rays non-parallel, in other words, more like your eyes, you can see depth, you can perceive depth better. That's how we do it. That's one of the ways we perceive depth, is based on the fact that the rays coming into your eyes are not parallel, right? And therefore our sense of depth is enhanced. Now, if I try to make the rays non-parallel to more mimic the human visual system, that's called perspective projection. That's what perspective projection is. It's trying to be more realistic. And it does like affect real life, so to speak. Has anybody ever noticed that when you look at a football game, right, everybody here looks at football games and rugby games and all that stuff on a TV, or I look at basketball games. The playing field, when you look at it on TV, it looks much bigger than when you see it in real life. Has anybody ever noticed that? Like when you go to a real football field or a real basketball court, I'm always surprised, like, oh wow, it's so much smaller in real life than it is on the TV. Has anybody else ever noticed that? It is, isn't it? It's very strange. I remember the first time, like, I was like, this is weird. Like, why does it look so much bigger on the TV than in reality? Well, now you know. It's the difference between parallel and perspective projection. So when you're looking at a TV, you're getting two images of the football field that are exactly the same. They're using parallel rays, so to speak. But when you look at the football field in reality, you're getting two different non-parallel rays. You're using perspective projection in real life, but if you look at a TV, you're getting two of exactly the same images. And you're getting a parallel projection when you're watching a TV. So that's a consequence of using parallel projection. Things look bigger and more distant when you use parallel projection, like things. Like everything looks bigger and more distant. Yeah. It's hard to get your head around, but it's fun. It's fun to know. Like I always wondered that. So back to the whatever we're talking about. The Shear Warp algorithm. It's possible to incorporate
perspective projection by doing the shear and a scale of the slices. So the slices are sheared and then they're scaled, so they're shrunk. They're getting closer together as you go further and further away from the viewpoint. Yeah, it's just a, it's a part of the original algorithm, and it's a good thing to know. And to make it even more confusing, perspective projection has another name. Now that's a pub quiz question, like a super duper advanced pub quiz question. What's the other name for perspective projection? I'm mentioning this because if you look at the paper, I hope that some of you actually read the paper. There's a paper that describes this in all the detail. Like maybe you didn't understand something I said today. You could look at the paper for the details in a slower fashion. There's a different, they don't use the term perspective projection. Any advanced pub quiz computer science graph. This is never going to be on a pub quiz. It's too advanced. You can tell I hate pub quizzes. I suck at pub quizzes because they're always like the history, like what happened to the Roman Empire, and actors and actresses and stuff like that, or sports. There's never a question about computer graphics on there. Anyways, it's called orthographic projection, also in some texts and some papers, perspective projection. And I don't think you talked about it that much in the computer graphics class here, because it's kind of an advanced topic, and you might not have even gotten that far in that one semester class. Okay, so to wrap up that algorithm, it's fast, easy to implement, it handles perspective projection. But there are trade-offs, right? Whenever you gain computation speed, you're trading off either accuracy or memory footprint. There's always those three trade-offs. So here the reconstruction is bilinear as opposed to trilinear, which makes it slightly less accurate. The voxel to pixel ratio, this magic property that makes everything so fast, which is a great thing, also can cause problems with zooming, right? Because you're not sampling, your sampling rate goes down when you zoom in. And here are some images of the shear warp algorithm, some volume rendering using the shear warp factorization. Some more images. Here's like some images comparing traditional ray casting with the shear warp. Right, here's somebody zooming in. This is ray casting, the slow version, so to speak. And then this is the fast shear warp algorithm. So you can see it's there's some aliasing artifacts. And this is zooming in somewhere too. But I think it's zooming in right here, maybe. And you can see that there are some aliasing artifacts. And there's a copy of the paper on Blackboard, and there's this book chapter that also talks about it. And just for fun, I have a video as well. This is a video it's another volume rendering demonstration video. It's one of my all-time favorites. And it's a nice summary. It's nice to see the volume rendering alive rather than in these static slides, right? But volume rendering is not meant to be shown in static slides all the time. It's meant to be interactive, and it's meant to be alive. And this video summarizes a lot of the things that we talk about in a really nice way, right? So it's showing
more like state-of-the-art volume rendering, which is very fast, right? This is 20 frames a second. It's showing different transfer functions, right? It's showing the classification, the applied classification, right? Classifying the voxels into different tissues. Right? It shows using different transfer functions like maximum intensity projection for the vessels, right? Or changing the transfer function to show some other information, a different view of the 3D data. It's also a focus and context visualization, where the focus is the blood vessels and the context is the bone matter, for example. So it's bringing a lot of concepts together, and it's bringing them together like in a lively way, as opposed to just a bunch of static slides. So the 3D visualization is really, really interesting when you can rotate the volume, right? It's more interesting. So there's the brain with surrounding tissue. It's too bad it's not Halloween to show this on Halloween. RTVR means real-time volume rendering. So that's an example of direct volume rendering that we talked about. Right, focusing on different subsets of the data, adjusting the transfer function, right, to adjusting the opacity, the dimension of the transfer function. That's another focus and context style transfer function. Here, that's a special transfer function that focuses on contours, so that the borders between objects. Right, that's an example of summation, or that's sort of like X-ray. Looks a little bit like an X-ray. An example of maximum intensity projection. And then combining techniques. So that's like peeling off a layer, or slicing. In some ways it's like slicing. Right? And then interactively adjusting the transfer function so you can peel off different layers and see inside the volume. Indigo?
That's at the start, that's a Java.
This is a Java library.
It's not normally the language choice for rendering.
It is not. Java is not the usual language. So the usual language, the most common language is C++. And the libraries that you typically encounter for assignment 2 are C++ libraries. Yeah. So that happened to be a Java one. It also shows you that it's possible to write fast software in Java. But that's another kind of interesting aspect. Any questions about that? So it's a lot of information. If you do have questions, you can just ask at the next lecture. It doesn't have to be today, right? You might be reviewing for something and trying to understand it. I guess you're going to have questions when be closer to the exam time. Yeah. Okay, and now I can hand out the feedback sheet for assignment 1. They're in alphabetical order of surname. Please keep them that way, right? There are 70 of them, so if they're not sorted, then it will take forever to find them. Thank you very much. You're free to go, you're free to go. Just might want to wait for your feedback sheet.